Hi guys, welcome back to the CCNA video series. In this video, we're going to have a look at STP port roles, port states and tiebreakers. We're also going to be diving in to how STP responds to topology changes and how long it takes for convergence to take place when a link goes up or a link goes down. So the objectives: understand what the port roles are, understand what port states are, understand how we can use the designated port and root port tiebreakers and what scenarios they would be used in. So to begin with, let's have a look at port role. So all a port role is, it's a specific role that a port plays within the spanning tree topology. So to begin with, we have the root port. The root port is just a local port on a switch. Every non-root switch, so not the root bridge, but every non-root switch has one. And so the root bridge, so not the root bridge, so the root port is just the port which is part of the lowest cost path to reach that root bridge. So as an example, this switch has got a root port and so does this switch. This port is counted as the root port because this port is part or included in as part of the lowest cost path presented to this switch to reach the root bridge. This port is also another feasible way to reach the root bridge, but it has a higher STP cost than this path. That's the reason why this path is chosen. Now we move on to the designated port, and it's just a switch on the local segment or on the local link with the lowest cost path to reach the root bridge. And there's always one designated port per segment. So if we look at our topology, we can see there's one DP there, another designated port there, another one there, etc. Now the designated port, both the designated port and the root port, they're both in a forwarding state. They're both sending and receiving traffic and learning MAC addresses. I guess the real main difference between a designated port and a root port is that the designated port, especially with STP, this isn't the same with rapid spanning tree, which we will discuss in a later video. But with the good old-fashioned STP, it's the designated port which forwards on BPDUs. So with STP, BPDUs are forwarded downstream, not upstream. So you will never see a BPDU forwarded out a root port. And though the way that this would work is the root bridge is going to send BPDUs or configuration BPDUs every 2 seconds. Since there's this interface. Now obviously 002, the reason why we still have to have BPDUs over this interface or this link is just so that the 002 knows that there is a alternative path to reach the root bridge. If 002 were to cease receiving BPDUs, then it would bring this link over here, which is currently blocking, into the forwarding state, and then we'd have a loop. But the BPDU would travel down to 003, who would then change a few fields and forward it over to 002. So now 002 is receiving BPDUs on this link and this link. Hence the reason why it knows that there's two paths to reach the root bridge and know that this path is still valid. Then we have the non-designated port, and this port in the STP topology is not a root port or a designated port, meaning it's going to be put into the blocking state. So this port isn't really used for anything. Is in the blocking state, the switch knows that it's probably an alternative path to reach the root bridge because it is receiving BPDUs listing the root bridge's bridge ID inside those BPDUs over that link. The disabled port, this is a port on the switch which is shut down administratively. So that means that someone actually went onto that switch and used a command shutdown, and that port isn't included in the STP topology. The three main ports included in the STP topology are going to be root port, designated port, and non-designated port. And like I said before, those ports, they all perform some sort of specific role or specific function within the STP topology. Now we're going on to port states. So the difference between port roles and port states is the port role is the function or the role that port is playing in the STP topology. It could be a designated port, it could be a root port. The port state, however, this is what state the port is currently in, what the port is currently doing. So if the port is in a state of blocking, it means that it will not pass traffic or learn MAC addresses. This is a stable state. So usually ports will either stay in this state or they would only come out of this state if they're going to transition into the forwarding state. Now the only ports that will move from blocking into forwarding will be designated ports or root ports. We have the listening state, which is a transitional state, and by default a port will stay in this state for the forward delay timer. and that forward delay timer is 15 seconds. So by default, a port will stay in the listening state. It will not forward traffic or learn MAC addresses, but it does send and receive BPDU. So it's thinking about moving to the forwarding state. Now, if it doesn't move to the forwarding state, it will go back down to the blocking state. Then we have the learning state. The switch will populate the MAC address table with any receive frames. So that means that the switch still isn't forwarding traffic out of a port in the learning state. Again, a port will stay in this state for about 15 seconds, but any traffic it receives is now learning the MAC addresses of that traffic, putting them in the MAC address table, and associating those MAC addresses with those ports. And then we have the forwarding state. So the reason why this impacts us, and especially impacts how fast STP is because once the STP topology has been chosen, once we've chosen the root bridge, our designated ports or root ports, the designated ports and the root ports, they're still in the blocking state because they're not passing any traffic yet. They move from the blocking state to the listening state to the learning state and then to the forwarding state. So it takes 30 seconds for those ports to go from blocking into forwarding. Now, 20 years ago, that was probably fine. However, nowadays, that is totally unacceptable. Hence the reason why there was a new version of STP which was brought out, Rapid Span Entry Protocol, and we will discuss that in a later video. But as you can see, this is the difference between port state and port role, because port role just defines what that port is going to be doing. Port state just defines how is that port operating at the moment. Is it blocking? Is it listening? Is it learning? Is it forwarding? Etc. And forwarding, we're going to forward frames, learn MAC addresses, etc. And if it's a designated port, then obviously we're going to be forwarding those BPDUs, because with STP, we cannot forward or send BPDUs upstream. Now, to see how those ports can impact, especially on the speed of conversions, let's have a look at some topology changes. So obviously, we know, okay, look, if it takes 30 seconds for our network to originally come up, maybe that isn't too bad, but these network devices, they're going to be on 24/7. So hopefully, once they've come up, they won't have to go through the STP election process again, because nothing's going to change. It's going to be stable. Let's have a look at how long it takes STP to reconverge or converge once there has been a change in the network. Okay, so imagine this sort of scenario. Switch 002, its root port goes down, and it immediately detects this failure because it's a direct failure. So this is the topology change process on a direct link failure. He knows, because he's been receiving BPDUs all along over this link, that he can reach the root bridge via this link. So what does it do? Does it go straight to forwarding? No. It still has to go through the listening and learning state. So for 30 seconds, guys, for 30 seconds, the devices which connect to this switch are going to be without any connection to the network at all. They will be able to communicate with each other, but not with the rest of the network. It takes 30 seconds for that port to actually come up, go into forwarding, and then we make that port our root port. And the reason why convergence time takes 30 seconds, because it's twice the forward delay timer. So we stay in the listening state for the duration of the forward delay timer, then we stay in the learning state for the duration of the forward delay timer. And so this is a configurable value. By default, it's 15 seconds. We can make it a bit faster, we can make it a bit slower. I don't know why you would want to make it slower. You probably want to make it faster, so that we stay in those states for at least amount of time. But that's how long by default it will take for that port to go forward. Even though that guy 002 knows there's no other route, or there's no other link to the root bridge. I've only got one other route. He still has to stay in those states for 30 seconds, and then can become a forwarding port. So the state would be forwarding. Currently, that is the state of the port. The port is sending and receiving traffic, learning MAC addresses, etc. And the port role is going to be a root port. The reason why is because its role is to provide the local switch with the fastest or quickest path to reach the root bridge. Now let's have a look at a topology change for an indirect link failure. Again, this is going to be a lot slower, and you'll see why in a second. And to be fair, it's because of the way that STP operates. So in this case, the root port fails on switch 003, and so we've changed our topology around. So if you go from here, we had the root port originally as being over here, that link there. In this case, I've changed the topology around. So in this case, this link is the root port, this link is the root port. Because this switch over this LAN segment has got the lowest bridge priority or lowest bridge ID, it's become designated port. He's in the non-designated port state, meaning that he's not sending BPDUs over to the switch, and that is vital to this discussion, especially when we're talking about this type of failure. So obviously 003 has lost this link to the root bridge, and it is the designated port for the segment between 002 and 003, so it's the one who's forwarding BPDUs. And because it stopped receiving all BPDUs listing 001 as the root bridge, he now believes, wait a minute, there's nobody else who I've received BPDUs from listing a root bridge better than me. So guess what? I am the root bridge now. So now he actually starts sending what we call inferior BPDUs. An inferior BPDU lists root bridge information which is actually worse than the current root bridge that we have. So in this case, 003 is going to be sending BPDUs, configuration BPDUs, to 002, saying, I am root, I am the root bridge, I am the root bridge. And to be fair, you know what he's going to do? He's going to ignore them. That's right, he's going to ignore them for 20 seconds. For 20 seconds for the max age timer, he's going to ignore those BPDUs. And he knows it's an inferior BPDU because he's like, this guy, he's listing himself as the root bridge, but the BPD information that I'm receiving that I've got saved on my device is listing 001 was a bridge priority of 200 as the root bridge, so he's obviously better. I'm going to ignore 003 for the time being. So 002 will just ignore these BPDUs as they are inferior BPDUs. After 20 seconds, so this is the max age timer, so again, it was 20, so if a device receives inferior BPDUs for the duration of the max age timer, once that timer has expired, then switch 002 realizes something is up. He is going to transition to the listening state, and he's going to then forward a superior BPDU over to 003. He's going to forward it over to 003, saying, look, buddy, I think you're a bit confused. You're saying that you're the root, but there's actually a better root bridge out there already in our network topology. Then, after going through the listening and learning phase, they both go through the states, etc. 003, it transitions that port to the forwarding state after, let's say, 50 seconds. Because you have to remember, 20 seconds for the max timer to expire by default, which means that I'm going to ignore you. Okay, wait a minute. You're listening to the wrong information, buddy. I'm going to forward you now a BPDU with the correct info. 15 seconds for the listening, 15 seconds for the learning. So it takes 50 seconds for 003 to recover from this topology change. That's almost a full minute without network connectivity. And to be fair, if you got that in an enterprise now, people would be screaming at you over the phone. That is not acceptable. It may, like I said before, it may have been okay 20 years ago, but in 2020, that is not an acceptable outage. It's too slow. And so 50 seconds for the link to come up, and obviously it takes 30 seconds for 002 to transition that port into the forwarding state and make it a designated port, because there has to be one per segment. If he's root, I have to be the designated. And to be fair, is that when these guys are forwarding BPDUs, they actually list their port role in those BPDUs as well, so he will know that that guy is the root port. The effects of the topology change. So obviously we saw how long it takes for convergence to take place. 30 seconds if it's a direct failure, and if that switch is currently receiving BPDUs on an alternate link, it takes 50 seconds if there's a direct failure, but that switch isn't receiving BPDUs of its alternate link. It therefore thinks it's the root bridge, will send inferior BPDUs to its neighbors, and then when its neighbor notifies him, it takes another 30 seconds for it to transition into the forwarding state. So when a topology change occurs, so this could be a link going up or down, we're going to say non-edge ports. So ports which are connected to our endpoint devices, and we configure spanning tree PORTFAST. So PORTFAST, again, that's a feature we'll talk about in a second. But a non-edge port, a port is considered an edge port when that port has got PORTFAST enabled on that port. We'll talk about PORTFAST in a second. I'll talk for the reason why we need that. But in this case, switches will send out a topology change notification BPDU saying that something has changed in the network. All switches that receive this topology change notification will set the MAC address aging timer to be equal to the forwarding delay timer. Because obviously something's changed in the network. We can't keep the same MAC table entries. We have to somehow have a quick way to dispose of those entries and load of new entries. And so it sets the MAC aging timer equal to 15 seconds by default. Again, this just depends on the duration of your forward delay timer. Then that topology change notification is sent upstream until it hits the root bridge, and the root bridge will send a BPDU to all the switches in the network with the TC bit or the topology change bit set. This is for the duration of max H plus 4 delay, so for 35 seconds I'm going to send this BPDU with the TC bit set in the flag field. And this is to quickly edge out old entries so that we can update the MAC address table quickly with new entries. So any device which receives this topology change notification, this topology change BPDU will set the MAC address aging timer for all of his entries to 15 seconds. This way we can clear any old entries really quickly and populate the MAC address table with new entries. During this period of 35 seconds, the MAC table will be slightly unstable, but it needs to be so that we can clear out old entries and put in new entries, because by default the MAC address aging time is 5 minutes. And this allows for automatic relearning of MAC addresses without an engineer needing to go to each switch and clearing the MAC address table manually. So let's see this process in action. So in this case, this link has gone down on this switch over here. It sends a topology change notification. So when a switch receives a topology change notification, obviously it sets the MAC aging timer to 15 seconds or equal to the forward delay timer. It then also sends back a topology change acknowledgement saying that I've received your topology change notification. You don't have to send it to me, because what happens if it doesn't receive a TCA back, it will keep sending these TCN BPDUs. This is the root bridge, so it gets all the way up to the root bridge, and then the root bridge just essentially floods the entire network with a topology change BPDU. So this is a BPDU, a configuration BPDU with the topology change bit set. This will receive by all the devices. So if any device within our network hasn't received the TCN BPDU, they will now receive a TC BPDU and set their MAC address aging timer to be equal to the forward delay timer, or 15 seconds by default. Now, through these examples, can you see an issue with STP? I mean, obviously it's good that it blocks the redundant link, stop loops from happening, but can you see it's very, very slow? It takes at least 30 seconds for a port to move from blocking to forwarding. Okay, obviously when we have our election, that's the one thing where, I mean, like, we could be satisfied with saying, okay, look, after the election process, we know it's going to take 30 seconds for everything to become forwarding. That's okay. So what I may just do is that's okay for now, and then obviously afterwards it should be stable. But as you can see, if anything changes, a link goes up or a link goes down, that causes a topology change to be sent out. And obviously if a switch needs to then move a port from blocking into forwarding, or make a non-designated port into a root port or into a designated port, that's going to take a long time. And this actually causes a major issue when we have our ports which connect to endpoints. And that means that anytime we plug in a computer, anytime we plug in an AP, anytime we plug in a surveillance camera, it will take 30 seconds for that port to go into forwarding. 30 seconds. And you're thinking, that doesn't make any sense, because I can understand with other switches because there could be a loop. But if I plug in my computer, it's not going to loop around because it's only a single connection. That doesn't make any sense. And like I said before, that because endpoints are unlikely to send BPDUs, it's highly unlikely that a loop will occur. I mean, is there any way that we could solve this issue? And the answer is STP or span tree PORTFAST. This is a feature which we can enable on our you would enable on your ports which connect to endpoints. And basically what it does is simple as this. It allows the port to move from blocking state into the forwarding state instantly. No listening, no learning, just from blocking into forwarding. And obviously that's the reason why you would only enable it on ports which plug into your endpoint, because if you enable this on a port which plugs into a switch, you actually can cause a temporary loop. And so the way that it works, okay, we can enable PORTFAST on ports which connect to endpoints. If we were to enable PORTFAST on a port which connects to a switch, and let's say this device over here receives a BPDU. Because it's received a BPDU, it's now going to put that port into the blocking state and then move, if it needs to put that port back into forwarding, to the listening and learning states. So that is pretty good. So PORTFAST, it means that this computer, this server, when we plug those devices into the switch, they will come up straight away. If we were to enable PORTFAST on this port over here and plug in another switch, as soon as this guy receives a BPDU, it's going to then go back to the way that span tree usually moves from blocking into forwarding state. So as you can see, this is very good. You may also be able to you can actually enable STP PORTFAST for trunk links. I know what you're thinking, why would I want to enable it for a trunk link? The primary reason is if you have virtual host in your environment. So a virtual host can actually have a virtual switch inside of it, and this allows you to send tag traffic to the virtual host. I've seen this in the place that I work. That's the way that we set up our connections to our virtual host, because chances are you'll have different VLANs for different servers, and then that way you can use one link and support all of your servers on your virtual host. Now, we've looked at port state, port roles, how those relate, and what a port role is, difference between a port role and a port state. We've seen STP convergence, why it's so slow. Let's have a look at the root port and the designated port tiebreaker. So obviously the root port is chosen based on lowest cost path to the root bridge, or lowest MAC address if there's a tie, lowest neighbor MAC address, the same as the designated port. So the designated port is going to be the switch with the lowest cost to reach the root bridge, or if there's a tie, the switch with the lowest MAC address. However, how about when a switch has got two paths to reach the root bridge? Okay. What is going to be the tiebreaker then? So in this case, this switch has got two paths to reach the root bridge, but they both go through the same switch. So lowest path cost or lowest neighboring MAC address isn't going to work because they're both going to tie. So then the first tiebreaker we have is going to be port priority. So port priority is a feature which is configurable on an interface, is STP priority, etc. And in this case, the neighboring interface with the lowest port priority will be selected as the root port. So in this example, as you can see, we have two ports here, one with a port priority of 120, one with a port priority of 100. Switch over here picks up that this port over here should be the root port, the reason being because its neighbor has got a priority of 100 on this port, but a priority of 120 out of this port. So pick this port as the root port. And then if we go down to the last tiebreaker, which is going to be lowest interface number, it literally just means the lowest interface number. So in this case, both of these devices are tied. However, out this link is plugged into FA0/1. Out this link is plugged into FA0/2. FA0/1 is lower than FA0/2. Now this port now becomes the root port, in that this is on the neighbor device the lowest physical numbered port number. And so literally those are the tiebreakers. And like I said, you wouldn't really see these tiebreakers in real life. The reason being is because if we wanted to connect two links into the same switch, we will use something called ether channel to combine those links. More about ether channel later, but that's the reason why we would never see, or very unlikely that we would see this kind of scenario in real life. PVST Plus, what's that? Okay, so obviously Cisco switches, we know they support VLANs. And what Cisco switches allow us to do, and this is with like most other vendors, I've worked with HP, Juniper, etc., they do the same thing, and that we can actually have, or we can configure STP on a per VLAN basis. So that means we can have a separate STP topology created for every single VLAN. And this is good because this allows us to make use of our redundant links by making different switches in our topology root bridge for different VLANs. The only issue is that depending on how many VLANs we have, so because there's a separate topology for each VLAN, we need to keep a separate STP topology tree in memory for every single VLAN. So if you have a lot of VLANs, this may take up quite a lot of memory on your switch. Again, it just depends, but the benefit is that we can actually load balance traffic now across redundant links. So as an example, I could have this STP topology configured for VLAN 10 and this STP topology configured for VLAN 20. So this way, for the VLAN 10 topology, this link is blocked by making use of these two links. That is the root bridge. And as you can see, we can have different root bridges, and a switch can have a different root port per VLAN. So in this case, for VLAN 10, this guy's not even the root bridge. He's got a root port. Let's say this is a designated port and this is a non-designated port. For VLAN 20, this guy is actually the root bridge, and those same ports are in the forwarding state for VLAN 20. And then we block this link over there. We have a designated port and a non-designated port. So as you can see, a designated port and then a non-designated port over here. So as you can see, you can have a different STP topology per VLAN, allowing us to load balance. And that means that a port can be blocking traffic for, let's say, VLAN 10, but then allowing traffic over that port for VLAN 20, making better use of our links. And that's all there is to it. So we've looked at port roles, port states. We've seen how STP recovers from a link failure or a link going up or down, the STP convergence process, a topology change. We've seen the reason why we're going to use PORTFAST, so that we can put those ports which plug into endpoints straight into the forwarding state. Again, if we receive a BPDU on one of those links, then we'll go through listing and learning it and then back into forwarding. And obviously we've seen that even though it takes seconds, so seconds for the STP topology to be created and chosen, it then takes 30 seconds for those ports to actually become active and start forwarding traffic. Now in the next video, we're going to have a look at configuring STP. So we're going to look at a 3-switch or a 2-switch topology. We'll look at configuring the different values related to STP, so things like route bridge, secondary route bridge, port cost, etc., all that sort of good stuff. If you found this video useful and have enjoyed this content, then please subscribe to my channel. If you found this video useful, then please share so that we can get high quality IT training to the masses free of charge. Thank you very much for viewing.